Okay, what we want to do is let me just go through and explain a little bit about the questions. I know we did the lab and we turned in the applications of principles, but I want to make sure that you understand the concepts behind it, just in preparation for our lab final. So in the first question, when we talk about the test for chloride and sulfate, why would the addition of acid help with the solvation of other types of solids? So, as you know, when we look at these guys, they're going to be insoluble, okay? And even when we add acid, they're going to remain insoluble. And the reason these three will remain insoluble is that HCl, HBr, and HI, these are all strong acids. Okay? So nothing's going to happen. It's basically going to stay completely solvated, and so the chloride's available to still react with the silver. However, let's take a look at some of the other possibilities. We might have carbonate in there, we might have phosphate, we might have sulfite. With carbonate, when it dissociates, remember, this carbonate will react with acid to form water and carbon dioxide gas. What that means is that I'm going to be depleting my concentration of carbonate, which means based on Le Chatelier, my solid here will continue to dissolve. Okay? What about if we look at something like silver phosphate? Well, remember, silver phosphate, if we look at the effects of acid, phosphate will form phosphoric acid. This is a weak acid, okay, which means it won't dissociate. So again, what happens is with the addition of nitric acid, this will actually reduce the concentration of phosphate, making silver phosphate more soluble. Finally, what about something like silver sulfide? Okay, again, my sulfide reacts with acid to form H2S. Okay, so again, if it's soluble, it's a weak acid, but a very insoluble, and so most of it will come out as a gas. So the reason we add acid is that all of the other possible solids have anions that react with H+. Okay? And likewise, if you look at barium sulfate, if you compare that, again, we're looking at barium carbonate, barium sulfide, okay, etc. Okay, barium phosphate, again, you're going to be looking at anions that react with acid. Okay, so let's take a quick look then at number 2. Okay, for experiment 9, number 2, remember we have an unknown compound that's going to react with barium chloride and it forms a white precipitate. So what are all the possible formulas of the white precipitate that we could obtain? So chlorides, remember, chlorides, everything's soluble except when it's paired with silver, mercury 1, or lead 2. So if this compound, this unknown compound, had a silver cation, a mercury 1 cation, or a lead 2 cation, it will form a white precipitate. Conversely, if X has an anion that forms a precipitate with barium, then you would get a white precipitate as well. So what are all those anions that would form a precipitate with barium? That would be sulfate, so you'd get barium sulfate, or your white precipitate could be barium carbonate, or it could be barium phosphate. So these 6 are the possible formulas for the white precipitate based on what we've been working with. If you look at number 3, it says a moderate test, okay, for sulfate is to be expected even if you don't have sulfate, you only have sulfite. Well, remember, the oxygen in the air is enough to actually oxidize sulfite into sulfate. So when you test your solution and it only has sulfite, you'll still have, a positive test. Not a strongly positive one, but slightly positive, because some of the sulfite that you already have is going to oxidize into sulfate. And if you think about it, that's one of the reasons why we don't make the sulfite solution for you. We just give you the solid and you make it fresh, just to avoid giving you a solution that has been exposed enough to air that you get a lot of sulfite present. Okay, so for number 4, why can't we have sulfite and sulfide in the same reaction? Okay, so in the presence of acid, your sulfide gets oxidized to sulfur. Your sulfite gets reduced to sulfur. So let's balance this out. Sulfite, this is a +4. Okay, so goes to sulfur 0. All right, have one of those. I have 3 oxygens here. I'm under acidic solution, so I'm going to put 3 waters. Okay, then I need 4 electrons here. All right, and I need, this is 6 hydrogens. Okay, so 3 oxygens, 6 hydrogens. This is a +4, goes to 0, so that's going to be 4 electrons there. Okay, now let's take a look at sulfide. So this is +2 electrons. I need a 2 here. So we have SO3, 2 minus, plus 6 acids, plus 2 sulfides, goes to a total of 3 sulfur zeros plus 3 waters. Okay, so why can't we have them in a solution? Because that will get oxidized and reduce that. Okay, now let's do the next one. Okay, so number 5. Okay, and the sulfite gets reduced, so acts as an oxidant. Okay, so let's take a look at number 5. If we look at number 5, and you're looking at XS, excess iron 2. So let's take a look and find out why. So why is excess iron 2 necessary? Okay, so let's take a look at the equation. Alright, so you need excess for two reasons. Okay, one. Okay, first of all, you need 3 times as much iron 2 as nitrate. And we don't even know how much nitrate we're putting in there. So we need excess just to make sure that we have our reaction. And 2, we want to avoid, okay, we want to make sure by using excess iron 2 that there is enough iron 2 even if we have oxidation, if we have air oxidation. Oxidation, where iron 2 goes to iron 3. So we want to avoid that one. But this one, we'll write down the equation. And the equation is on page 88. And we had to add a lot of acid. We had your sulfuric acid. Okay. You had your sample with nitrate. You had a freshly made solution of iron 2 sulfate. Okay. And what happens is you get this redox reaction. This only happens at the interface. Okay. So you form this, and then with the excess iron 2, you're going to form this complex. Okay? And this is what we need. This is brown, and it's at the interface. And this is what we observe. Okay? So we need at least 3 to form NO. And then with the excess, you're going to form this complex. So that's why we need excess. 1, we want to make sure that we don't do the bare minimum amount because we don't want oxidation. But you need 3 times as much plus excess to form the complex. Okay? So even if we hadn't completed it, when we have our lab final, you should still be able to explain it. Okay? Alright, let's move on. Last question. Alright. So, at number 6, okay, for the last problem, it asks, how can you tell the difference between a bicarbonate ion and a carbonate ion? And basically, we know bicarbonate, this is my pKa, and for carbonic acid, this is the pKa for bicarbonate. And what this means, though, if you look at your bases, this means that this is more basic than the bicarbonate. So if we just check the pH of the solution, and we know the concentration, then you will know whether or not you have carbonate or bicarbonate.